Okay, so welcome back to the second part of this course. So yesterday we spoke about better-quasi-orderings, and today in this first lecture I'll give a general introduction to ordinal analysis, which initially will not have a connection to what we saw yesterday, but then in the final lecture hopefully things will come together. So ordinal analysis is a method from proof theory, which nowadays has many different applications, but I guess traditionally the main point was to prove the consistency of axiom systems. So let's start with that. And let's start by looking at a consistency question that doesn't quite have to do with ordinal analysis yet, but it will set us on the right track, I hope. How do you prove the consistency of I sigma 1 in Peano arithmetic? So Peano arithmetic, you have basic axioms for the natural numbers and then full induction for all properties that you can define in the language of first-order arithmetic. And in I sigma 1, you have induction only for formulas where you don't have alternations of unbounded quantifiers, but only a single unbounded quantifier, maybe an existential quantifier at the beginning of your formula that defines the property that you want to establish for induction. And I sigma 1 is quite a small fragment compared to all of PA, so you should be able to prove its consistency in the full theory. And how do you actually do it? I guess the obvious idea would be to formalize the soundness proof. So you assume you have a proof of contradiction in I sigma 1. You want to exclude that, but assume that you have one. And then you start at the axioms that appear in that proof. These are true as recognized in Peano arithmetic. And then you want to go through the proof and show that all formulas that occur in the proof are true. So the end formula cannot be 0 equals 1 or your favorite contradiction because this one is not true. But for this, you have to say that formulas are true, and then you run into the obstacle when you try to do that naively that you don't have a global truth predicate in arithmetic that would cover all formulas of arithmetic by Tarski's result. So what do you do? Well, there are partial truth predicates that cover all formulas of some limited quantifier complexity, so you could have the idea to use one of these. And as far as the axioms are concerned, everything is fine because the axioms of I sigma 1 indeed have limited quantifier complexity, so then they can be covered by a truth predicate, a partial truth predicate that you can work with, that you can define. But there's one issue that remains, namely even if the axioms and maybe the end formula that is proved in a formal derivation have limited quantifier complexity, the derivation could make detours through formulas of arbitrary quantifier complexity, of one that you cannot bound from the outset. So the full proof of contradiction, potential proof of contradiction that you look at, might contain formulas of high quantifier complexity that are not covered by your partial truth predicate. So what do you do now? Well, one solution is to apply cut elimination, and what cut elimination does is remove precisely these detours through formulas of high quantifier complexity. Let's take a look at how this works. And if you want to do something like cut elimination, you really want to work with formal proofs, then you should probably fix one particular proof calculus. And a very elegant one for this purpose is tight-style sequent calculus. So first of all, the formulas that you work with in these proofs are supposed to be formulas in negation normal form. So you have negation only in front of atoms. And then outside of the atoms, you have conjunction, disjunctions, existential, and universal quantifier. And you cannot eliminate one in favor of the other because you're not allowed to apply negations except in front of atoms. And also when you want to negate a formula, then you don't put a negation sign in front of the formula and leave it there, but rather you put it there in the first place, but then you push it through via De Morgan's rules and eliminate double negations, and then you have, once again, a formula in negation normal form. Okay, and then out of these formulas you form a sequence, and these sequences are just finite sets of formulas, and the intuition is that you should read them as disjunctions. So a sequence, a finite set of formulas, says one of the formulas, at least one of the formulas in this set here. True. Right? And there's an example on the slide as well. So the induction axiom, you can of course write it down as an implication. But if you want to exploit the sequence structure, then you could write it down like this. So this is a sequence consisting of 3 formulas, and you typically omit the set brackets when you write down sequence. So this is a set containing these 3 formulas, and it's interpreted disjunctively. So it says either this first premise of induction is violated, and the formula phi that you want to establish by induction does not hold at 0, or there is a problem at some successor step, so there's some x such that phi holds at x, but not at the successor, or if these two are not valid, so the premises of induction do hold, then you do actually get phi for all x, which is conclusion of induction. So that's just an example for a sequence. And then you get a complete proof system if you just put 6 simple rules into place. So this first rule here says for each atomic formula, either this formula holds or it does not hold, and then you can always put side formulas. This is just weakening the sequence. So it says either theta or not theta or something from gamma, and gamma can be anything. Then you can introduce conjunctions if you have established that phi 0 holds or something from gamma, and you have established that phi 1 holds or something from gamma. Then you know that the conjunction holds, or maybe something from gamma satisfied. And then similarly, you can introduce a conjunction, disjunction from one of the disjuncts. You can introduce a universal quantifier from such a statement where the critical variable was free. You can introduce an existential quantifier. And then you have this cut rule, which says if you have proved on the one hand that either something from gamma holds or phi holds, and you've also proved that either something from gamma holds or not phi holds, then something from gamma must hold because, well, not both of these can be satisfied. So let's say maybe phi was false, then this first premise says you. We will see that the cut rule is not actually needed to get a complete proof system, but we will also see that it's still very important to have it available when you start doing certain things, and then you can eliminate it later. Okay? And what I could also maybe say is that there are a lot of variants of sequence calculus that you can use for different purposes. So in particular, sequence here, for me, they are just finite sets of formulas. For some purposes, it's better to consider finite sequences of formulas, where formulas can occur more than once, and maybe the order of formulas even matters. Or you consider finite multisets, where formulas can occur more than once, but the order doesn't matter. But here we just consider sets, and we don't count multiplicity. And then you have this really elegant calculus, which has maybe the only drawback that it's not suitable for intuitionistic logic. So due to this negation normal form thing, somehow classical logic is inherently built into it. And you can, of course, write down sequence calculi for intuitionistic logic, but then they have, well, some more rules than this. So if you're only interested in classical logic, I think this is a beautiful framework to choose. Okay, so maybe one thing that I want to mention, because it will come up in a moment, is that if you're looking, for example, at the rule of existential introduction, then we should mention that this gamma can be any set of formulas. And in particular, it's allowed that this existential formula here also occurs in gamma. So it's allowed that this formula is in gamma. And when that's the case, I can, of course, write gamma as some gamma prime without that formula plus that formula added to it. So then we could write gamma as gamma prime together with that formula. Once again, I'm omitting set brackets or the union symbol in favor of just a comma, just a list of the formulas that are in this finite set. And then the rule takes the following shape. So if I now put gamma prime, comma, this existential formula in the place of gamma, then what I have is gamma prime and this existential formula and this instance phi of t in the premise. And from that, I derive gamma prime together with this existential formula. So far, that's just the gamma that occurs here. And now I could put the existential formula again, but it's already there, and I'm considering sets. So it doesn't make a difference if I put it into a set again. So I will not write it a second time, right? So I can also, this here would be a valid instance of this rule of existential introduction. And that's very important because typically when you prove existential statements in classical logic, you have more than one candidate on which you want to introduce the existential quantifier. And that corresponds to the fact that in Herbron's theorem, the Herbron disjunctions, which gives you the terms that are candidate witnesses for the existential quantifier, they have length more than one, right? So you can eliminate in Herbron's theorem in a suitable situation an existential statement in form of a finite disjunction over terms, but there are several candidate terms. And if this existential formula was not allowed to occur up here, then you would always have Herbron disjunctions of length 1, which would not be. That's important, and it will also come up in one of the proofs that I'll sketch in the following. Okay, so now there is this very important, very classical theorem of Gentzen, which says that if a sequence can be proved with the cut rule, then it can also be proved without it. And why is that so important? It's important because in all rules other than cut, the premises are subformulas of the conclusion. So you can see that here, right? For example, in the case of the disjunction, the premise phi I is a subformula of the disjunction phi 0 or phi 1. And so what that means is that if you know the quantifier complexity that is of the statement that is proved at the root of your proof tree, then you have a bound on the quantifier complexity of all the formulas that can occur in your proof, but not if the cut rule was present. Right? So that's why it's important to eliminate cuts. Right? Okay. So yeah, let's maybe prove this cut elimination theorem. And I'm not sure, can I switch off the projector for a moment, and will it switch on smoothly? You know how to do that? Otherwise, we'll just leave it on. Okay, thanks. Thanks a lot. First step successful, switching it off. Maybe before I do that, how many people have seen the proof of cut elimination in a setting like this? Okay. Most people, not all people though. Well, let's still do it. Okay. So let's start with some notation. Start by switching on the light. So this here denotes that a sequence gamma can be proved by a proof tree of height at most n, where all cut formulas have complexity strictly below d. That means gamma has a proof of height most n with cut formulas phi only of height below d. And then the first big ingredient to eliminate cuts is a result called reduction. So let's maybe call that proposition. And let's say we have proved the premises of cut. So we have proved with some height m that not phi holds or gamma, and we have proved with height n that phi holds. So we've proved phi in its negation, and let's say that phi is disjunctive. So that means that phi starts with an existential quantifier, or the outermost connective is a disjunction, or maybe phi could also be atomic. You could also admit that at this point here. And you want to assume that the height of phi is less than or equal to d. And the conclusion is that then you can get a proof of height m plus n. So you add the two proof heights, you keep the same cut rank of gamma. Yeah? And the point is that this bound d, the subscript here, only allows cuts over formulas that have height strictly below d. But here in the assumptions, phi could have rank equal to d. So if you would reach gamma by a cut, then this d would be to increase to d plus 1. And the point is, for cut elimination, that you can do this, you can reach gamma without doing the cut over phi. And the proof is an induction on n. So on the height of one of the assumptions, and that's why I demanded that phi is disjunctive, because you have to do the induction on the right assumption, on the correct assumption. And now within this induction, you argue by case distinction on the last rule that was used to reach that conclusion, gamma or phi. Your case distinction in the proof of this premise here. And there were 6 different rules, so you could have 6 or maybe 7 cases. But we'll only look at one, because in all the other cases, you just pass on the induction hypothesis and nothing really happens. And the case where something happens is the one where this phi is an existential formula. And the last rule here introduced that existential formula. So before applying that last rule, and hence by a proof of height at most n minus 1, what you had deduced was gamma, comma, phi, comma, some instance of that. Right? And then from this instance, phi psi t of phi, you have introduced the existential quantifier. And now you'll see that this is exactly the form of the rule that I've written down here, right? So the existential formula phi that you have in the conclusion is kept in the premise, and you add some instance. It's very important to consider this case where the existential formula is kept in the premise. If that case didn't exist, then the bounds would be smaller than the ones that you get, but that would be a mistake. Good. So what do you do now? Write this down. Okay. Now we have this assumption here that gamma or not phi holds. And since these sequences are interpreted as disjunctions, they only become weaker if I add more formulas in, right? Because a disjunction of more formulas is something weaker. And so this is also reflected in the proof calculus, as you can easily check that if with height m you can derive this, then with the same height m, you can also derive the same sequence where you have added in another. And now you want to apply the induction hypothesis, which you can do because this proof here has a lower height, a smaller height. And the induction hypothesis allows you to, so to speak, cut away the phi without increasing the cut rank from D to D. So by induction hypothesis, from this, you get with height m plus n minus 1 and cut rank still bounded by D, that you have gamma or psi t. The application of the induction hypothesis, where you have taken that formula additionally into your type formula. Right. And now there's one more thing to do, namely you have to consider what the negation of phi is. And we are considering formulas in negation normal form only. So if phi was this existential formula, then if we form the negation normal form of negation, that will be a universal quantifier over the negation of psi. Okay. And now you use this assumption that you can prove with height m, gamma, or this universal formula again. And you argue that from this, you also get, with the same height m, this negated instance here for the t that you were considering before. Okay? And semantically, that should be true. If gamma is true or the universal statement is true, then either gamma is true or any given instance of the universal formula is true. But you have to check that it works with the same proof height, and that's a result called inversion. So let me maybe write that down. And the idea is that in the proof of this universal formula, whenever you have introduced the universal quantifier, the premise had established this for a free variable, and since the variable was free, you could simply substitute this term t here for the free variable, and then the entire proof would stay valid, and you would get a proof of this. Okay. And now there's only one final thing to do. So you now have gamma or psi of t, and you have gamma or not psi of t, and so you can cut psi of t away. So by cut, you now get with bound m plus n, which is an upper bound, strictly above these two, gamma. And maybe one thing to observe is that the rank of the cut formula now, psi of t, is strictly smaller than the rank of the full existential formula, which was less than or equal d. So now the formula that you cut over has rank strictly below d, and that's why you're allowed to keep the d. So you push the cut somehow upwards in the proof and replace it by cuts over less complex forms. That was that. And then let's also, even though many of you have seen it, I want to do it, now derive the cut elimination theorem. Which says that if you can derive some sequent gamma by a tree of height n, and with cuts bounded by d plus 1, then you can reduce the cut rank to d, prove the same sequent, but the cost is exponential. So the proof can become exponentially. And how does that work? Well, it's an induction on n, again, on the height of this given proof. And it's a case distinction, again, on the last rule that was used in this proof. And since you want to eliminate cuts, I guess it's not too unexpected that the crucial case is the one where the last rule was a cut. And so the premises are that with height reduced at least by 1, you have proved gamma or phi, and you have also proved gamma or not phi. And the rank of this cut formula here must be strictly below the bound that is given here, strictly below d plus 1, so it must be less than or equal d. So you are in the situation of the resultant cut reduction. Okay. And now what you do, you apply the induction hypothesis to the two premises. And you learn that with height 2 to the n minus 1, but cut rank reduced to d, you have proved gamma or phi. And also with the same bounds, you have proved gamma or not phi. But now you can apply the reduction theorem. So by reduction, what you get is that if you now add these two heights, 2 to the n minus 1 plus 2 to the n minus 1, then you can keep the cut bound d and still eliminate the cut over phi. And of course, 2 to the n minus 1 plus 2 to the n minus 1 is 2 to the n, which is the bound that was promised in the cut elimination case. So now we can switch on the slides again, if we can. Please enter password. You know the password. On the computer. Very good. Excellent. Okay. So maybe the first thing to say is that we have this theorem at the bottom of the slides due to Orevkov and independently to Stadtman, which says that what we did here is essentially optimal in terms of complexity. So cuts bring super exponential speed up because here we had one exponential for bringing down the cut rank by one number. And if you want to eliminate all the cuts and bring the rank down from d to 0, then you have to do that d many times. So you have a stack of d exponentials. So you have the super exponential function. And that is one way to see that even though cuts can be eliminated in principle, in practice they are necessary because proofs with cuts, or let's say the other way around, proofs without cuts can just be so much longer than proofs with cuts. And one place where you can see that is if you want to give a direct translation from your favorite proof calculus to sequent calculus. And your favorite proof calculus might well include modus ponens. Let me just share that as well for people who have maybe not worked with sequent calculus that much. So if you have modus ponens, how would you recover that in sequent calculus? So the idea is you have a proof of phi and you have a proof of phi implies psi. And first of all, you have to think about what phi implies psi means in negation normal form. Well, it means not phi or psi. And from these two, somehow in sequent calculus, you want to reach psi. So how do you do that? So you can show that you have not psi or psi for any psi. It's only an axiom for atomic psi, but by induction of psi, you get it for any formula. And then from that, you can reach phi and not psi, or psi, where the phi comes from up here. And so you introduce a conjunction. You have derived phi and you have derived not psi. You can introduce the conjunction, and this psi here just stays. But now phi and not psi is the negation of what you had up here. Okay, because if you negate, okay, by De Morgan, this will be a conjunction. The double negation falls away, and the negation stays here with the psi. And then you can not use another board for that. Cut away this formula here with this formula here, and you have your proof of psi. That's how the cut rule would allow you to recover modus ponens, and that's why if you want to write down a direct translation from some different proof calculus into sequent calculus, it's good to have the cut rule present. Okay, so that's about the consistency of I sigma 1. Now, what about the consistency of full Peano arithmetic? And I'm following Gentzen and also Schutte in the way I present this. So, of course, by Gödel's theorem, we know that the consistency of Peano arithmetic cannot be proved in PA itself. But what is it about the things that we saw so far that would go wrong if we try and replace I sigma 1 by Peano arithmetic? Well, the problem is that in PA you have all the induction axioms and they have unbounded quantifier complexity. So even if you eliminate detours by cut elimination, your proofs may still contain formulas of unbounded complexity as axioms, and so you run into the same problem that you don't have a global truth predicate. Now, there is a very radical step to resolve this due to Hilbert, and this is to pass to infinite proofs and to use the omega rule, which is a rule with infinitely many premises, and it says that if you have one proof which says that phi holds of 0 or something from gamma holds, and you have a different proof which says that phi holds of 1 or something from gamma holds, and you have this for each numeral number, and you can combine these infinitely many proofs into a proof that the universal statement for all natural numbers x phi holds, or still something from gamma holds, is true. So proofs are now infinite, and of course you cannot write them down in practice, but they are still a very useful tool for mathematical investigations. And specifically for us, the point is that in this system you can now prove induction. And I won't do that on the blackboard because the idea is really quite simple. So if you have the premises of induction, that phi holds of 0, and whenever it holds for x, it also holds for x plus 1, then you can really prove that phi holds of n for each fixed n, right? Because for 0 you have it given already, and if you have a proof that phi of n holds, then you can use that the induction step is given, taking you from n to n plus 1, to give a different proof that phi holds of n plus 1 as well. So you can reach each fixed finite number, but then you can put all these proofs together via the omega rule to get a proof that phi holds for all x, which is the conclusion. So then this issue that I just mentioned, that PA has induction axioms of unbounded complexity, it falls away because there are no axioms anymore. You just prove them in this infinitary system. And also this system still admits cut elimination, essentially by the same proof. In fact, things even become a bit simpler because you don't have free variables anymore. Right? So when you introduce a universal quantifier in usual first-order logic, then you have this variable condition, which can be a bit subtle. But if you introduce it that way, this universal quantifier, then you don't have any variables around. And in fact, you can set up the entire proof calculus sentences only. You don't need formulas with free variables anymore, which actually simplifies things rather than making them more complicated. Okay, so what do we learn from that? Well, in order to say that, we have to talk a little bit about infinite ordinals, because we now have infinite proof trees and we still want to control their heights in some way. And so we need to look at ordinals or ordinal notation systems, and the one that is presented here on the slide depends on the notion of Cantor normal form. So I guess most people will have seen that the basic operation of arithmetic, addition, multiplication, exponentiation, can be defined essentially by the same recursive clauses on infinite ordinals as well. And then it turns out that if you consider exponentiation to the base omega, this operation has a fixed point, and the minimal such fixed point is called epsilon 0. And then what you may have also seen is Cantor's normal form theorem, that any ordinal can be written in this form here as a sum of exponentials with weakly decreasing coefficients. And now the idea is that you can use this Cantor normal form, or this idea, to generate all ordinals, or to generate notations for all ordinals below this first fixed point epsilon 0. Namely, you construct a term system where you say whenever you have terms in this order, whatever the order is going to be, then you can also write down this term here, and this will then also be a term in your term system. Yeah, so what's the order? It's lexicographic comparison. In fact, hereditary lexicographic comparison. You assume that you already know how to compare the exponents, and then you know how to compare with others. And yeah, maybe I should say that this list could be empty. So you start with the empty sum, which is the ordinal 0, and that's. And then for later use, we will also consider notations up to epsilon alpha, which is the alpha fixed point of ordinal exponentiation, where gamma is some externally given fixed linear order. And the way you do that is you take exactly the same terms, except that you throw in constants at the beginning, epsilon beta, for all elements beta of this given order alpha here. Maybe one small thing you should do is you should exclude terms of this form here, because epsilon beta is supposed to be a fixed point of this operation. So if you take the exponential, this will just be equal to the term epsilon beta, and so you don't want to add another term to it. Okay. Yeah, this was quite quick. Are there questions about that? Yes, if you just want to have a term system, then you can do that for any linear order. Sometimes you don't want to assume that things are well-founded because it's just by quantify over sets. You don't want to. Yeah, then let's go on. So we also have cut eliminations, as I mentioned, for cut elimination for these infinite proofs. And part A of this theorem is essentially what we saw before on the blackboard. So if you have an infinite proof of height at most alpha with cut formulas of height strictly below n+1, so we have this here, then we can reduce the cut rank at the cost of an exponential. In fact, the base of the exponentiation could also be 2 rather than omega. Right? And the proof is exactly the same. Nothing changes. And then we'll use also this part B, which is maybe a bit less known, namely what happens if you have, so here you have a global bound on the cuts that can appear in your proof. And of course, when you start with finite proofs, then there will only be finitely many cuts in such a finite proof, so you have a bound on the complexity of the cut formulas. But let's assume you get your infinite proof from somewhere else, not from a finite proof, then it could contain cuts over formulas of all finite complexities. Infinite proof can contain infinitely many cuts. Formulas can have any complexity. So let's say we have no bound on the cuts, and hence I write omega as sort of a trivial bound if all the formula ranks are finite. So what's happening then if I have a proof of gamma of height alpha with no bounds on cuts? Well, it turns out that I can still eliminate all the cuts, and that's the 0, because now all the cut formulas should have ranked strictly below 0, so there are no cut formulas left. But then the height of the proof can increase to these epsilon numbers. Maybe it's worth doing the proof of that as well. And I think this will be the only other proof in this lecture that I do in detail. Okay, so let's take this assumption here. With height alpha, no bound on cuts, I have derived gamma. And let's say the case, so I'm again doing an induction on the alpha and the case distinction. And the case that I want to consider is, of course, again, the case of a cut. So let's assume with some height beta smaller than alpha, I have derived gamma and phi, or phi, as well as gamma or not phi, and then in the last step I have applied a cut over this formula phi to reach gamma. And now I apply the induction hypothesis, and it tells me that in these proofs of the premises I can eliminate all the cuts, and then with height epsilon beta and no cuts I have proved gamma or phi. And also I've proved gamma or not phi. So what can I do now? Well, the only thing that really comes to mind is I have to cut away gamma. I have to cut away phi if I want to reach the gamma. So by cut, what I now get is by a proof tree of height 1 more, I reach gamma. And what's the bound on the cuts? Well, the only cut is the 1 over phi. So I can do that if I assign cut rank of phi plus 1. And now I can use part A. So now I have a finite bound on the cut rank because I only had one cut in the proof now. And I know how to reduce finite bounds by part A by one step, but then all the way down to 0. So what I get in the end is, let's maybe just put some eta as the height of the tree, and we'll calculate the eta later. I eliminate all the cuts. I get my gamma. And so what's the eta? Well, the eta somehow has this previous bound epsilon beta plus 1. And then for each level of cuts that I eliminated, there is one exponential. So then I have a tower of exponentials, and at the top this epsilon beta plus 1. And I have rank of phi plus 1 many other. But now the point is that all this is below epsilon alpha, if beta is below alpha, because these epsilon numbers are fixed points. So it doesn't matter how many exponentials I have, the exponentials don't do anything to this number. If you like, if you haven't seen it before, you can think a bit more about it. Now that's really what you get, and that's what it says on the slide. Maybe one other thing to say at this point. So cut elimination is of course important in ordinal analysis, and you can continue building extensions of B with higher ordinal bounds and do more and more complicated things. And that's one thing that you do in what's called predicative ordinal analysis. But then also ordinal analysis is much more than cut elimination, and I wanted to say that. So for example, if you analyze theories like cryptic-Platek set theory that are impredicative, then cut elimination will only be a small part of what you do. And maybe the more important ingredient is called collapsing. And what that means is that in general, the proof trees that you work with will then be uncountably infinite and collapsing transforms these uncountably infinite proof trees into countable proof trees. I think that's also a really beautiful procedure, but we won't see it here. I just wanted to mention it because many people have at some point seen the ordinal analysis of Peano arithmetic, and then maybe you think that, okay, they are looking at cuts all the time, but it's not the only thing that we do in ordinal analysis. Yeah, so what are the consequences of this cut elimination procedure? Maybe the first thing to say is, at the beginning, when we are looking at the consistency of I sigma 1, we were working with finite proofs only. And there it was pretty clear that the cut elimination procedure was a primitive recursive procedure and could easily be formalized in theories like PA or I sigma 1 itself, or weaker theories even. But now we are operating on infinite proofs, and it's maybe less clear how these transformations of infinite proofs, cut elimination for infinite proofs, can be formalized in weak theories, but it turns out that you can do it. And there are different approaches. So one approach that's maybe conceptually appealing is that you don't look at arbitrary infinite proofs, but you only look at computable or maybe only at primitive recursive infinite proofs. And then rather than working with the infinite objects themselves, you work with the computable indices for these objects. And you can formalize that. I particularly like a paper by Wilfried Buchholz, which will be on the reading list as well. Maybe I'll say a word more about this. I think it's really a very elegant approach to formalization. But in any case, what you learn is that this cut elimination procedure for infinite proofs can be formalized in weak theories, such as, let's say, I sigma 1. Okay. And then one thing that you learn from that, and a very classical result, is that over I sigma 1, the following are equivalent. First of all, Peano arithmetic is found for sigma 0, 1 formulas. In particular, it's consistent. And then secondly, epsilon 0, the first fixed point of ordinal exponentiation, or let's say the term notation system for this fixed point, is primitive recursively well-founded, which means that we don't have primitive recursive sequences that are infinitely descending. That's one conclusion that you can draw from that. But for the final lecture that I give after the coffee break, it's somewhat different consequences of cut elimination that are important. And let's look at these first. Next, sorry. Okay. So here we have a theorem that was proved first by Alberto Marconi and Antonio Montalban. In fact, not by cut elimination, but by computability theoretic methods. But then it was shortly afterwards proved by Bahari Afshari and Michael Ratjen using these cut elimination techniques. And maybe I can say there are many more theorems of a similar shape. And some of these, we only know how to prove them via ordinal analysis, and we don't have a computability proof for these. And also, what I like about the proofs via ordinal analysis is that the ordinal analysis that is needed is already there. You just have to translate it a little bit and bring it into the right setting, and then you get all sorts of different results of this form. So what does the result say? Well, it's now an equivalence of reverse mathematics. And the first statement in equivalence says that every set has an omega Turing jump. And that's the main axiom of a system typically denoted by ACA 0 plus. And the second statement is quite easily seen to be equivalent to it. So the main point of the theorem is the equivalence with 3. But the second statement says that every set lies in an omega model of ACA naught, or in a coded omega model of ACA naught. And let's maybe just recall it orally. So these models of second-order arithmetic, they have a first-order part, which looks something like the natural numbers. And then they have a second-order part consisting of subsets of the natural numbers. And the first-order part could, in general, be a non-standard model of the natural numbers. And omega model means that the first-order part is exactly the standard natural number. And then the crucial third statement is whenever alpha is a well-ordered, then so is this term notation system epsilon alpha that describes the alpha fixed point of And so now how does ordinal analysis help you to prove this? Well, the more difficult direction is to see that 3 implies the other 2 statements. So let's show that 3 implies 2. That's the reason why I put 2 rather than 1, because it has the right form to be derived by ordinal analysis. So we want to derive 2. 2 says every set lies in an omega model of ACA 0. So it says, in some sense, there is a model, right? And we know by completeness and soundness that having a model is the same as being consistent. Right? And now we don't just want any model, we want an omega model. So this corresponds to consistency not for usual proofs, but to consistency for omega proofs with this omega rule that we have. And there is an omega completeness result for these proofs and models. So in order to show that these omega models required by 2 exist, you only need to know that there is no infinite proof of contradiction, no omega proof of contradiction from the theory that you want to have in your model, so from ACA naught. And it turns out, well, ordinal analysis does precisely that. It gives proofs of consistency, and it uses ordinal bounds that in order to do so. And it turns out that 3 provides precisely the bound. Yeah, maybe you want to clean the blackboard because I want to say, I give some more details about this. Namely, what I want to say is, so far we have seen the ordinal analysis of Peano arithmetic, and now we want a model of ACA naught. And well, Peano arithmetic and ACA naught are very closely connected. One is conservative over the other, and maybe you know the model theoretic construction that if you have a model of Peano arithmetic and you take the arithmetically definable subsets of that, then you get a model of ACA naught. But somehow this model theoretic construction is not something that we can use here, right? Because if I want to take the collection of arithmetically definable sets, then I already need quite a strong meta theory. This is nothing that we would do in RCA naught. So it turns out that using the ordinal analysis of PA directly is not what we need here. We really need an ordinal analysis for ACA naught itself, so in a second order language. And the crucial rule in that ordinal analysis of ACA naught looks like this. So you want to introduce a set quantifier. And the rule tells you that you can do that if you have the formula phi, where this existential set variable is witnessed by a comprehension term, this for arithmetical psi. And then it's quite easy to see how in such a calculus you would be able to derive arithmetical comprehension, simply because anything that's arithmetically definable now gives rise to via this rule here. And now we can maybe briefly think about the assignment of formula ranks here. And it turns out that if phi is arithmetical, you want to say that this formula starting with an existential set quantifier has rank omega, has infinite rank now. So it's not the height of the formula as a syntactic object, but you say when I encounter my first set quantifier, I assign rank omega. And you do that because this is now strictly bigger than the height of the formula in the premise. Because in the premise, everything is arithmetical, so no set quantifiers. And so this will have finite height. And that's the point for cut elimination. You want to eliminate a cut over the formula in the conclusion in favor of a cut over the formula in the premise. But for that, this formula should have smaller height. Right? And that's also why you get these bounds epsilon alpha and not some bounds below epsilon naught, because you have these infinite formula heights. And that's essentially the theorem, that's essentially part B of the theorem here. Right here, we did not have a bound on the finite cut heights, so we had a bound omega, and then we saw that these epsilon numbers come in. And that's the same, essentially. I have one quick thing that people could think about. We know that arithmetical comprehension is the same as just comprehension with the sigma 1 formulas. So you could think that maybe in this rule here, it's enough to put sigma 1 formulas, and then maybe you don't need the infinite formula. And then you would get bounds that are smaller than this epsilon alpha. And it's not going to work, but the question is why? So why do you need to allow arbitrary arithmetical formulas here, not just sigma 1? I think it's a subtle point, but it can also. Now, before the coffee break, let me show you, I think, just one last result here that we will also need in part 3. So this is a notation system a bit weaker than the ones, or quite a bit weaker than the one for epsilon alpha that we saw before. Namely, you now take a fixed order alpha, and you take exponents only from this fixed order. And what you then get is an order called omega to the alpha, where you simply have terms of this form, but you don't allow to iterate into the exponents, right? So you just have Cantor normal form terms with exponents from a fixed order. And then there's this theorem by Girard and Hurst, which says that also over RCA0, the following equivalent, arithmetical comprehension, and then this transformation here, whenever alpha is a well-ordered, so it's omega. Right, so in a sense, the omega corresponds to a one jump, and then epsilon alpha corresponds to the omega. This we will also need in part 3. Ordinal exponentiation is the same as arithmetical comprehension. And then just some reading for this. So there's a very nice survey in the Stanford Encyclopedia by Michael Reitjen and Sieg on proof theory, which focuses a lot on ordinal analysis. I think that's a good starting point if you want to read something on this. There's this very nice paper by Michael Reitjen. It's also very long, but it's a great read. I have a course on the ordinal analysis of Peano arithmetic that I try to keep quite short and self-contained. And this is this paper by Buchholz, and it's one of the most beautiful papers that I know. But you already have to know the ordinal analysis of Peano arithmetic quite well. And then it tells you how you can formalize that in weak systems. And with Buchholz has a particular writing style without too many explanations, but I think it's an extremely beautiful paper. Then these are the two proofs of the result that we saw, the one by Marcone and Montalban via computability theory, and the one by Afshari and Reitjen that I tried to summarize. And then finally, there is a lot of literature on well-ordering principles now. So well-ordering principles are these type of transformations, some order alpha into some order omega to the alpha that's computable from it, or some order alpha into another order epsilon alpha that's computable relative to it. And this is a survey paper on well-ordering principles. Now connect proof theory, computability theory, and reverse mathematics. That's it for the